All right, so Chris and Harry mentioned complexity of the code. And I want to start with complexity of chemistry. I'm not a chemistry engineer. I'm more of a mechanical engineer. So when I look at combustion for the first time, I had this feeling, whoa, there was something very complex with it. Here is a simple picture, and it's mostly applied for combustion, but it can be for any reacting simulation. If you look at hydrocarbons and you characterize the complexity of your fuel with the number of carbon atoms, well, to describe accurately the combustion or the oxidation of your hydrocarbon, you would need an increasing number of species for an increasing complexity, right? And if you go from methane, which is quite simple, to diesel fuel, you would end up with thousands of species. If I flip this chart and have the number of species as a x-axis and now as a y-axis I'm using CPU time, well, you can quite easily see that there is also a huge problem here. If we want to characterize more complex fuels or more complex configuration, you end up with a CPU time that is way higher than what you would have for a simple fuel. So there is an issue, and that was the motivation initially to work on reducing the impact of detailed chemistry on our CFD simulation. And the basic idea here of this presentation is to introduce two contributions. Actually, I will reuse what Henry was saying before. The first part is about trying to reduce the impact of the chemical mechanism. And this was work I did during my PhD. And that was more in the form of contribution to the code. So the work was already done, and there was all the process of integrating in the library. In the second part, I want to talk about something more in depth, more detail about the buts and nulls of solving the chemistry with the improved Jacobian or the reworked Jacobian. That was more, in a sense, an example of collaboration. So it was developed together. So let's start with this chemical mechanism, but my main message of my presentation is, in any case, that contributing to the library is very important, of course. Doing development of code is very important. This is not something, and you will see it with my examples, this is not something you can do alone and without help for, as we said before, maintenance, for example. So let's go there through these 2 points. And the first point is this complexity. As I was saying before, a lot of CPU time for a more detailed mechanism. But to give you some numbers, if you take a typical mechanism for oxidation of methane would be around 40 species. Well, if you activate chemistry, all of a sudden you multiply your CPU time by 10. So without reactions, a certain amount. If you add the reaction, times 10. Now, if you want to have, and again, this is my way to picture a chemical mechanism. I'm not, again, a chemist, so I had to see it in a different way, differently than just reaction. So I see it as a network of species. Every point is a species, and they are connected through reaction in a very big and complex network. I did that to understand the complexity, and I think it gives back the complexity in a way. If you use this mechanism, which is it is isooctane, well, you basically, when switching on the chemistry, you basically multiply your CPU time by 1,000, which in general is deemed unaffordable. You can't afford doing that. So how to solve, or at least partly solve this issue, well, that's where we did something to the library, to contribute to the library. To get to the contribution, I want first to explain how this is working in the library currently. So the way I picture it is that there are actually 2 big boxes where things happens for reactive simulation. There is the part of the CFD, handling transport equation, and there is a part where you solve the chemistry. In a bit more details, you have this CFD box and chemical box. The CFD box handles the transport, mixing, etc., and a certain source term. And the source term, you can find it back in the code if you want, here in orange. This is actually considered constant during the integration time of the CFD box. And it is computed somewhere else in my chemical box, where we assume that nothing's changing during this same time step. So it's called splitting scheme, where you basically assume no mixing, no transport to solve this set of ODEs. And this is done in the chemistry model library through the combustion models interface. So to get the complexity of these two boxes, basically you need to understand that for combustion, but also for many reactive systems, the set of ODE we need to solve is very difficult. It's nonlinear and stiff. And in general, stiffness comes from the large range of timescales you have. Typically for a combustion case, you will have very fast chemistry, but also very slow chemistry together, spanning a range of timescale that is way larger than typically what you would have for flow and transport. So from there you have complexity, but at the same time, if you're solving a chemical case, you want comprehensiveness. You want to make sure that your chemical system is accurately represented. So you want a lot of species, but to have your solution in a decent, in a reduced amount of time, you also want to get rid of as many species as possible. So there is this trade-off between the two, and that's where we wanted to include the work I did during my PhD, which is tabulation dynamic adaptive chemistry. Actually, it's a combination of two methods. There is a tabulation method and a mechanism reduction method, and I will go through the details of these two methods now. So you have, again, those two boxes, and for the transport equation, you need to solve this source term. So you have some conditions, some composition, mass fraction, temperature, and pressure that you need to send to the chemical box. Well, the first thing you can do with the tabulation algorithm is to try to retrieve previously computed result. This is expensive, so you want to store them, and if you retrieve the solution, it's way less expensive than going to the chemical box. So that's the first thing. Sometimes you can't retrieve, so you have to go to finding a solution. But then you go into a second step, and it's important again to understand why those chemical mechanisms are so big. They are big because they are comprehensive in terms of all the conditions you can apply them to. So you can use this mechanism in different equivalence ratio, temperature, pressure, but now we are in a specific cell for specific conditions. So you can extract part of your mechanism for the set of conditions you have. So instead of solving the entire mechanism, which we know is very costly, you just go through another box, reducing the mechanism to the set of species that are absolutely necessary to describe accurately your condition. Then you go to this chemical box. You will still pay quite an overhead to solve your set of ODE. And then you go back. Before going to the CFD box, you store your information. That was still costly. And then you go there. Right? So the tabulation algorithm that is used now is ISAT. It's a very well-known tabulation algorithm. It can be extended to other things. We'll come back to that in a second. And there are several mechanism reduction techniques that have been also implemented. And again, also that can be extended. We'll not show the video here. You will have this link. It explains how the mechanism reduction work. I invite you to just click on it whenever you have a chance. It's just showing you a case where you see how the network that we've seen before evolve according to time, showing that sometimes some species are used and then just discarded because they are not used anymore in the mechanism. Right. How is it set up in the library? Well, it's rather simple. You can, anytime you have a reacting solver, you can just select in the chemistry properties dictionary this method TDAC, and then you have two sub-dictionaries describing the settings for the tabulation and the mechanism reduction. Pretty simple, and there are several tutorials available where you can see different setups. Still, there is a lot of case-by-case settings needed, so sometimes it requires a little bit of research, let's say. I think it was said before there are critical needs and critical works to the library, and I think although I was the starting point for this contribution was during my PhD while I was doing engine simulation with Professor Tommaso Lucchini and Gianluca De Rico in Politecnico di Milano. My main motivation as a PhD student is not to produce a code that is easily maintainable. My first priority is to get this paper published. So I think it's very important to understand there is a huge difference of motivation, and whenever you want to contribute to your piece of code to the library, there is a lot of work to be done. And so this was also an example of the work to be done. It has to be reworked so that when you fit it in, it still works for other applications. It's also not bringing so much complexity as Andrew was mentioning before, and especially for ISAT, this requires a lot of effort. So now it's, as I was saying before, you can easily extend it for tabulation, for reduction methods. You can also, remember there were 2 intermediate boxes, but you can add other layers. If you want, for example, to take advantage of this different time scale, it's quite easy to just add another box and continue working on it. Still, there are things needed, and one of the things I wanted to work for a long time on, and still requires effort, or a PhD student, is this work on ISAT. ISAT can be very effective, but when you massively parallelize it, then it becomes more and more difficult to work with, especially because every processor will have its own table. So there are several techniques to take advantage of the parallelization, and this needs to be included at some point, especially if you want to move towards HPC. Right, so that was the first part on tabulation of dynamic adaptive chemistry. And actually, although my title refers to OpenFOAM 6, this was already included in OpenFOAM 5. Now, let's move to a little more details of the chemical box, something that happens in the chemical box with the what I call improved Jacobian or new Jacobian, whatever this means. I wanted to just bring very simply, and this is not exactly what happens, but I wanted to, in a simplified way, tell you where the Jacobian plays a role. So in this chemical box, you're solving a set of ODEs describing how the species mass fraction change in time. So you have the species mass fraction depending on a function of the species mass fraction, also temperature and pressure, that provides a reaction rate, right? Because of stiffness and nonlinearity, you want to solve that implicitly to make sure that it doesn't take very small time steps. So typically you would represent it like this. The result after the time step would be based on the result of the previous time step multiplied by a step size and your function, right? Simple, except that inversing this would be very, very difficult. So generally you linearize this, and there's where Jacobian plays a role. If you want to change this term into h multiplied by something you know plus the derivative of this by the species mass fraction, for example, and the difference, there is a Jacobian. This is the df dy, all right? Again, this is not exactly how it works in the ODE solver. This is way more complex, but it's a simplification to understand how semi-implicit would work. In the previous Jacobian, it worked quite well. I mean, there were no big issue with the Jacobian, but there were some limitations. For example, there were no terms in the Jacobian for the third body or general pressure-dependent effects. The temperature derivative also was through finite difference. And basically, in some cases, it led to instabilities despite the excellent ODE solvers that were implemented in the library. And so you had excellent ODE solvers, but they were provided with sometimes wrong information from the Jacobian. And because the Jacobian is central to making them work easier, then this would lead to instabilities. So, of course, having a new Jacobian, which is a kind of a core aspect of this chemical box, led to a major restructure of the code. I mean, to me, in my chemistry world of the library, this led to big change and especially for the reaction rates, where we had to add some new derivative terms, and those were all moved to the species library. Also, these new derivative and pressure-dependent terms were quite complicated to code. They were mostly inspired by combustion, but I will come back to that. Some new reaction rate from, for example, enzymatic or other kind of application would be even more complicated to code. And some new terms also had to be coded because of the temperature derivative in the thermo library. So a lot of different things, a lot of effort to get this right. The good part is that it provided better stabilities in many applications. If I take a very simple ChemFOAM case, now you can run it with much bigger time step and tolerances without crashing. And for the same accuracy, you could have your results much faster. For reacting foam, and I will come back to that in a second, for typical same quality of results, you could still see improvement in CPU time. Still, we had seen some issue, and I want to mention that now. We hoped and we thought having a new Jacobian would solve all our problems. Actually, it's never the case. But what we have learned in the process, and that's really what I wanted to call this idea of collaboration, is that we learned a lot during this process, is that, well, things didn't turn as we thought they would be. We had, for example, in reacting foam, things that didn't work as we expected. One of the first things is that, for example, we needed to add some adjustments to make sure, and I will come back to that in a second, to make sure the case could run. At the beginning, also, it was much slower because we were comparing things that were were not at the fair comparison. For example, tolerances defined in the previous Jacobian were not exactly the same as for the new Jacobian. So, yeah, it required a lot of effort to understand if things were working well. And of course, we thought it would be way more effective, but by including some additional terms, although you take them into account, it's also sometimes less effective than what you think. The side benefits, of course, is that whenever you do a work like this, you start thinking, okay, how could we rework the library to make it more effective? And this is a huge additional side benefit that you have. And another one that I mentioned just before, one of the few adjustments we did is to include the temperature clipping, because I didn't mention it before with the ODE solver, but during the process of solving your ODE, the ODE solver do intermediate steps, and sometimes it overshoots in temperature, for example, or in concentration, which means that you might go above or below a certain range of temperature where your thermodynamics is defined. But the ODE solver doesn't know he's solving something for thermodynamics, so we had to tell him, and clipping the temperature was the way to do it. I mentioned it before, one of the things that a new Jacobian brings is additional complexity in now adding new kinds of reaction rates. I give you here some examples. For example, enzymatic reaction rates provide a certain complexity in these derivative terms. They were not needed before. Now we need to bring them in the Jacobian, so you need to define them. So what it means is that whenever you want to add now functionality related to reaction rate, it means also an implementation overhead to get things right in the Jacobian. Right, so this was the two illustrations of the contribution I wanted to give to you with. First, something that illustrates more kind of a contribution and a difference between the work of a PhD student and the work that is needed to fit into a library with maintenance. And then a second illustration with this work on the Jacobian, where there was a continuous collaboration through the development. And to illustrate that, typically, something I'm not always very proud to show, but because it illustrates maybe my lack of effectiveness, I don't know. There was a lot of interaction with Henry to make things right. I'm pretty sure it's a bit of lack of effectiveness from my side, but it's also because there were so many things that needed to be reworked. So there is definitely something to be done to make these interaction easier, and I'm pretty sure Chris will mention that later today. There are other things I wanted to mention, because contributing, as we were saying, and as Henry also mentioned before, so you have a piece of code from maybe one of your PhD students or from yourself, you did your PhD, then it's not like an office you go and you drop your piece of code and that's done. There is a lot of things to be done to make sure that this can be a long-term contribution. Otherwise, as we mentioned before, this would be just loss of time. And then, of course, this contribution through what we have seen with Jacobian, I wouldn't have thought of many possible solutions or shortcuts. And though through this interaction, I think there are many good ideas that comes into, oh yeah, we should do this way, and this will be helpful to later application. So my three main conclusions for these talks are, first, it's very difficult to develop without help. You massively talked about maintenance issues, but I could also bring you an example about publishing. We wanted to, there are some complexity in setting things right for cases with reaction and kinetics, and we wanted to have an article about that on the website of the foundation. But of course, you know, as a professor, it was done in May, June. I was busy more with the exams, with other things related to academia, and so without any help from Chris, I couldn't make things correctly. Hopefully he followed up and say, oh, did you check this and that? Because otherwise it's just impossible to do. The second conclusion is that development opens sometimes Pandora's box. You just say, we're just going to do this. But then you see, a bit like I've shown with my network of species, it's connected to so many other things that you didn't think about that it makes sometimes things way more complicated than you anticipated. What it means is that it's never easy, and to me, I never understand how Henry can do that, to anticipate the amount of work needed to do a job. I can't do that. And the third point is that I wanted to insist that collaboration, contribution and development is very important. With the example of the side benefits, it's an additional example. Not only the development part is important, but the side benefits are also very important. So combining those through development is very, very important. I will close this talk with this. So basically, contributing, being a contributor is very important, but this is not something you can do without the help of the foundation. That's it.